In this lesson, let's spend some time in planning how best we could memorize the formulas that we have developed so far for the time of flight, for the range, and for the maximum height of a projectile. Let's take the simplest case first, where a ball is launched vertically upwards with a velocity of v0, and we have to find the time taken for the ball to land back on the ground. The time taken by the ball is 2v0 over g, and this formula you should try and remember. Just in case you forget, the derivation should take you less than a minute. We apply the second equation of motion along the y-axis. The initial and the final displacements are both zero as the ball lands back on the ground, and the acceleration is minus g. And from here we get t as 2v0 over g. This is our basic formula for the time of flight, and you will see how we will modify it for the different scenarios. Also, let's note down the basic height formula when a ball is launched vertically upwards with an initial velocity of v0. The height to which the ball rises is v0 squared over 2g, and this is also a formula that you should try and remember. And in case you don't, then apply the third equation of motion along the y-axis, which is the axis along which the ball rises. And we use the concept that at the very topmost position of its flight, the final velocity is 0. The initial displacement is 0 and the final displacement is the height h. The acceleration is minus g, and with this we obtain the height h as v0 squared over 2g. Now we have used our basic formulas for the time of flight and for the height h. Using these, let's see how we can get to the other formulas. Now this is a projectile that is fired from the ground, and it lands back on the ground to the same horizontal level. Now when a ball is launched vertically, the time of flight was 2v0 over g. Here we make v0 to v0y, the y component of velocity, as for the time of flight we apply the equations of motion along the y-axis. And v0y is v0 sine of theta for a projectile. So the time taken for a projectile ground to ground is v0 times sine of theta over g. So we have just modified the basic formula. For the same projectile, let's find the maximum height attained. The height formula for a ball launched vertically upwards was v0 squared over 2g. Again, we make v0 as v0y, the y component of velocity, as for the maximum height we apply the equations of motion along the y-axis. And v0y is v0 times sine of theta for a projectile. So the maximum height attained by the projectile ground to ground is v0 squared sine squared theta over 2g. Next we get to the inclined plane, and the basic time of flight is 2v0y over gy. Remember that we are considering motion along the y direction, which is not really the vertical direction. This time v0y is v0 sine of alpha, and the acceleration due to gravity along the y-axis is gy or g cos beta. So in the same basic formula, we are substituting components of velocity and acceleration along the y-axis. The maximum height formula is v0y squared over 2g. For the incline, we consider all components along the y-axis when computing the maximum height along the y-axis. v0y is v0 sine of alpha. So in the numerator, we get v0 squared sine squared alpha, and in the denominator, gy is g cos beta. With that, we get the maximum height formula as v0 squared sine squared alpha over 2g cos of beta. The horizontal velocity component along the x-axis is constant, v0x or v0 cos of theta, and this is due to the absence of acceleration along the x-axis. The range, therefore, is v0x times t, which is v0 cos of theta times the time of flight, and the time of flight is 2v0 sine of theta over g. And finally, we come to the range along an incline. And here you have to be a little careful. We use the same concept, which is that the horizontal velocity component in the horizontal direction, not the x direction, is constant, and that is v0x as marked here, which is v0 times cos of alpha plus beta, and this is due to the absence of acceleration along the horizontal direction. The time of flight of a projectile on an incline is 2v0 sine of alpha over g cos of beta. Multiplying the constant horizontal velocity v0x with the time of flight t gives us the horizontal range RH. This is not R but RH, the horizontal component of range. The range that we want to compute is along the incline, or R. Now RH is R cos beta, and that is equal to the constant horizontal velocity component v0x times the time of flight t. So we get R cos beta equals v0 cos of alpha plus beta times 2v0 sine of alpha over g cos beta. And with this, we obtain the range as v0 squared sine of alpha cos of alpha plus beta over g cos squared beta. Just understanding this small concept will save you a lot of effort required in memorizing the range equation. So now we have covered how to derive the formulas for the time of flight, maximum height, and range for projectiles launched ground to ground and on an incline. Just learn the basic formulas for the time of flight and height when a ball is launched vertically. The rest of the formulas are just variations of these. And as far as the range is concerned, use the concept that the horizontal range would be equal to the constant velocity component along the horizontal direction times the time of flight. To quickly remember the projectile formulas, go to the basic formulas and apply the components of velocity and acceleration in the corresponding directions.